Hey everyone, Mr. Boltri here bringing you video 1.5 in which we're going to do some graphical analysis. So in our last video, we came up with this nice graph which related the weight of my cat Echo versus the time after her adoption. So 0 months was her weight at adoption, and then we recorded her weight moving forward from there. With the goal of when she was adopted, she was underweight, and we're trying to finally get her to a weight of 6 kilograms, which is her target weight. So we have this graph. What can we do with it now? Well, the point of doing a graph is to be able to analyze the data. And there's 4 big things that you can do in terms of analyzing data. The first and maybe most important is to determine the underlying pattern, to figure out what's going on with the data. The second is to create an algebraic model or a mathematical equation for the data, because then from that we can interpret the meaning of the model and therefore understand the data better. And maybe most excitingly, we can use the model to make some predictions. So we're going to go through each of these 4 steps in the video, starting with determine the underlying pattern. So there's a lot of different patterns that the data could be, but the easiest one, the one that we're hoping all of the data is linear. So the first question that we need to ask ourselves is, does this data look like it's going in pretty much a straight line? And there's kind of one really good way to figure that out is just to throw a line on the data and see if it fits. So we're going to talk about lines of best fit. So our goal with a line of best fit is to put a line on the data to see if the data is linear, and then use that line to show the general trend in the data. So to show the general trend in the data, we want to go through as many data points as possible. And if the line can't go directly through every data point, we kind of want to even out the number of data points that are a little bit above the line and a little bit below the line. So this line very clearly is not a good representation of the data. It's not close to anything. But if I sort of start to move the line around a little bit, I can sort of try to pick a good starting point. And then once I have a good starting point, I can sort of try to play with the slope a little bit to try to see where I can get the slope to go through as many of the data points as possible, but keeping a different amount, try to find equal amounts above and below the line. So this looks like a pretty good line of best fit because it goes through quite a few of the data points. And then this one's a little bit below, but this one's quite a bit above. This one is just a tiny bit above, but this one's a tiny bit below too. So there seemed to be an equal number of points above the line and below the line. So this, I would say, is a good line of best fit. And you'll notice that it does not go through 0, 0, because it wouldn't make any sense in this experiment for it to go through 0, 0. And it doesn't even have to go through the first point. It just has to go through as many of the data points as possible with equal numbers above and below. So now that we have this good line of best fit, we can turn that into an algebraic model. Or another way to say that is we can write the equation for that line. And so I hope you remember from algebra class, what is the general equation for a linear function, or the general equation for a line? Hopefully you do remember that it's y equals m times x, or mx, plus b, where y is the vertical variable, x is the horizontal variable, m is the slope, and b is the vertical intercept. But like I said in my last video, in this class, we're not doing just random numbers, y and x. We're graphing actual things like weight and time. So instead of using y and x, I want you to use different variables that are more reflective of what is actually being graphed on the axes, like w for weight and t for time. So now we want to actually substitute in where we have m, we want to actually figure out the slope, and b, we want to actually put in the vertical intercept. So the vertical intercept is pretty easy. It's just where it crosses the vertical axis. So this is 2, 2.5, 3, 3.5. It's somewhere between 3.5 and 4, but closer to 3.5 than it is to 4. I would say that's about 3.7. So I can go ahead and put that in there. W equals slope times time plus 3.7. And then the next thing is going to be to calculate the slope. And I'm hoping you remember from algebra that slope is rise over run, which is the change in the vertical variable divided by the change in the horizontal variable. So in order to figure that out, we need to choose 2 points, calculate the change in weight, and then divide it by the change in time, the rise divided by the run. So let's choose 2 points. And hopefully you've noticed that these 2 points, there's something wrong with them. Because you have to choose 2 points that are on the line. If you don't choose 2 points that are on the line, you're going to be calculating the slope of a completely different line. So choosing 2 points on the line, this one, the line seems to go directly through this data point, and I'm going to choose this one. Even though it's not a data point, that is okay, as long as you clearly mark it and the line goes through that point, then if you find the slope between any 2 points in the line, you should be good to go. So I always like to label my points just so I don't get mixed up in the calculation process, and I would recommend that you do the same. So now that we have that, we just need to figure out the rise, the change in the vertical variable, the change in the weight, then divide it by the change in the run, the change in the horizontal variable, the change in the time. So to do that, my weights are, looks like it goes from 3.8 to 5, so I'll do 5 minus 3.8 to get the change there. And then the time goes from 1.5 to 13.5. So I'll keep the order the same. 5 minus 3.8, 13.5 minus 1.5, and I get 1.2 divided by 12. So in your math class, you might stop there because that is a fraction. But in this class, it's going to be a lot easier for us to compare values with different groups if we write our slopes as decimals. So I'd ask that you just simplify that all the way down to decimal form, and we get the slope as 0.1. Then we can go back and put that into our equation. And now we have an algebraic model that relates the weight versus time. We know that weight equals 0.1 times the time plus 3.7. Woo! So now what we get to do is we get to try to figure out, well, what does that mean? And when we try to figure out the meaning of the graph and the meaning of the model, we're looking mostly at 2 things. We're looking at the meaning of the vertical intercept and the meaning of the slope. And we'll do those one at a time. So looking at the vertical intercept first, that's where the line crosses the vertical axis. So that is, what is the weight at time 0 months? So we could interpret that as being when Echo was adopted, she weighed approximately 3.7 kilograms. And it's okay, though she actually weighed 3.5 kilograms, but it's okay that our line predicts that she would have weighed a little bit more, just because the line doesn't go exactly through every data point. But we can say approximately that was Echo's weight when she was adopted. And now slope is where things get a little bit more interesting, because the slope is 0.1. And one of the things that we can often do to try to figure out the meaning of the slope is to look at the units of the slope. So we said rise over run, that's going to be kilograms divided by months. 0.1 kilograms per month. So that another way to think about that is 0.1 kilograms per 1 month, which gets us thinking that maybe the meaning of the slope is, on average, because some months she went up a little bit more, some months she went up a little bit less, but on average, how much Echo's weight increased every month. So every month, on average, it seems like her weight is going up by 0.1 kilograms. And now that we have an algebraic model, and we kind of understand what it means, we can finally use it to make some predictions. So like I said at the beginning of the video, the vet did say that she's still a growing cat, and ultimately, she's probably going to weigh around 6 kilograms. So we've kind of set that as a target for how much she would like to weigh. So the question is, when is she going to be able to weigh 6 kilograms? So we can use this equation, W equals 0.1t plus 3.7, to figure out when she's going to weigh 6 kilograms. The 6 kilograms is a weight, so we're going to put it in for the weight. And then all we need to do is solve this linear equation. So I'm going to add the opposite to both sides, or subtract 3.7 from both sides. and then multiply by the reciprocal or divide by 0.1 on both sides, and I get that t equals 23. Now don't stop there. I'm not going to require that you answer in full sentences, but your answer should always have a box around it and include your units. So in answer to when will she reach her target weight of 6 kilograms, the answer is at 23 months. So we have about another year to go until she's at her target weight, but we don't want to rush it because a slow and steady increase of 0.1 kilograms per month is healthy for a growing calf. But once we get to about 2 years in, then she should finally be at her target weight. So hopefully you see the power of graphical analysis, not only to visualize your data and understand the pattern, but then also use that pattern to make predictions about what's going to happen in the future. So this is the end of video 1.5. Go Bears.